Hi everyone, I'm Tyler from University of Illinois. Today I'm going to present our work, Acto, automatic end-to-end testing for operation correctness of cloud system management. This is a collaboration between UIUC, IBM, and Cornell. Operation correctness is crucial to system reliability. Let me start by showing you a Zookeeper failure caused by its buggy operations. Let's suppose we have a Zookeeper cluster of 3 nodes, each one with a volume. Then a scale down operation is issued to delete the 3rd Zookeeper node. Due to data safety considerations, the 3rd volume is not deleted. Afterwards, a scale up operation is issued to create the 3rd Zookeeper node. Since there's already an existing volume there, the new node just directly reuses the old volume. The Zookeeper operation is supposed to correctly update the Zookeeper membership list that's stored in the old volume so that the new node can join the cluster. However, a bug in the operation code prevents it from doing so. This causes the new Zookeeper node failing to start, leaving the Zookeeper cluster in a permanent error state, and all the subsequent scaling operations would fail. In this failure, as we can see, the Zookeeper's behavior is correct, where it refuses to start on the inconsistent membership list. Kubernetes' behavior is also correct. The bug is in the Zookeeper operation code, where it cannot correctly manage the Zookeeper membership list. Nowadays, cloud systems are increasingly being managed by those automatic operation programs, termed operators. The scaling example for the Zookeeper is just one of the mission-critical operations performed by the Zookeeper operator. Today, most cloud systems have operators to manage them on top of Kubernetes. There's a thriving ecosystem around operators. We have Operator Hub, which is like GitHub, providing a platform for sharing operators. Operator Framework is an SDK for developing operators. We have books teaching how to write operator and white paper standardizing the cloud-native operator design pattern. There are many international events, such as Operator Day, co-located with the KubeCon. Next, let me explain the de facto operator design pattern, which implements this declarative operation interface. An operator continuously reconciles the managed system from the current state to the desired state. In Kubernetes, the desired states can be easily declared by assigning values to the properties exposed by the operation interface. This is an example of the Zookeeper state declaration containing properties such as replica, image, and persistent storage. System states are represented by the state objects on the management platform, such as pods and volumes on Kubernetes. Operations then can be easily issued by declaring a new desired state. For example, to upscale the Zookeeper cluster from 3 nodes to 5 nodes, users only need to change the replica property from 3 to 5. The Zookeeper operator then performs a series of complex actions. It first needs to add 2 more pods and 2 more volumes. And finally, it needs to correctly update the membership list that's stored on each Zookeeper node. As we can see, such a declarative interface greatly reduces the human operation overhead. Operator bugs are causing production failures. There are many recent incidents caused by bugs in operators in important cloud systems, such as Flink, Kafka, MongoDB, and Spark. And in this paper, we make the following contributions. First, we present Acto, an automatic end-to-end testing technique for cloud system operators. It defines and checks 3 operation correctness properties. First, operators should always reconcile the managed system to the desired states. Second, operators should recover the system from error states. And third, operators should be always resilient to operation errors. We designed and implemented Acto as a push-button tool and is open-sourced it on GitHub. So far, Acto has detected 56 serious bugs in 11 popular Kubernetes operators. Many of them have been confirmed and fixed. Recall this Zookeeper operator bug in the beginning. In this bug, the error manifests in the Zookeeper system itself rather than in the operator. This is why Acto runs end-to-end tests for operators to reason about the whole system behavior. However, automatically testing operators end-to-end is very challenging. First, how to explore the different transitions of the system states, from different starting states to different desired states. Second, how to generate effective state declarations to explore the enormous system space and also trigger state transitions. Third, how to automatically check if the system states are valid or not. And finally, we aim to develop a push-button tool that can be readily applied to different types and implementations of operators. Next, let me show you how we design Acto to address all the challenges. First, how does Acto explore different transitions of states? Acto models the operations as state transitions. Each operation is a pair of the current state and the new state declaration. An operation applies the new state declaration on top of the current state and drives the system state to the next state. Let's denote state declaration as D and system states as S. To explore state transitions starting from different starting states, Acto keeps applying the new state declaration on top of the previous existing system states. This way, we can get a test campaign with an operation sequence. Remember that the second correctness property for operator is to recover the system from error states. In a test campaign, when Acto detects the system is in an error state, it tests if the operator is able to recover the system from this error state by applying the previous healthy state declaration and check if the system can recover or not. If the system can recover, then the subsequent operations would continue from there. Otherwise, the Acto raises an alarm. Lastly, operators are supposed to follow the level triggering principle. That is, operators should always reconcile the system to the same desired state, given the same state declaration, no matter what is the starting state. In a test campaign, Acto tests this level triggering principle by applying the same state declaration on top of different starting states. Note that all these different kinds of state transitions are triggered by generating new state declarations. So how does Acto effectively generate state declarations to find bugs in operators? First, Acto satisfies the value constraints to pass the basic schema validation. The reason is that if the value constraints are not satisfied, the declarations are directly rejected by API server without even reaching to the operator. Second, the state space for each property is enormous, and to effectively explore the space, Acto only exercises representative operation scenarios for each property. Third, Acto satisfies the property predicates to trigger the state transitions. If the property predicates are not satisfied, then the state declaration are essentially no ops. Next, let me show you how Acto does each of them one by one. First, how does Acto satisfy the value constraints? Fortunately, the value constraints are already encoded in operation interface specification. In Kubernetes, they are encoded in the format of the Open API schema. In this example of the Open API schema, it defines the constraints for the replica property, where the type needs to be integer and the value range to be minimum of 1. The Open API schema defines the constraints for all the properties exposed by the operation interface, and Acto generates value that satisfies these constraints. Second, to exercise the representative scenarios for each property, Acto needs to first understand the property semantics. However, automatically understanding the property semantics is challenging because different operators implement the interface differently. Our key insight is that the property values eventually gets mapped to the Kubernetes core resources. For example, the ZK volume claim value is eventually mapped to this persistent volume claim Kubernetes resource, which defines how the storage is used. Since Acto already understands the semantics of this persistent volume claim, by mapping the ZK volume claim property to it, then Acto can understand the property semantics. The mapping can be obtained via the structure analysis. If the structure of the property is the same as the Kubernetes core resource, then Acto establishes the mapping between these two. For more accurate mapping, Acto uses static tint analysis over the operator source code. In the static tint analysis, the initial tints are the property values in the operator program. The tints propagate through data flow dependencies. If the tints hit the Kubernetes core resource types, then Acto maps the property to the Kubernetes core resource. Once we have the mapping, Acto uses scenario-based value generator for the properties. Acto not only generates valid scenarios to test the functional correctness, but also generates erroneous scenarios to test if the operators are resilient to operation errors. For example, Acto generates a scenario to scale down and scale up for the replica property. And this scenario helped Acto to detect the zookeeper operator bug in the beginning. Acto also generates the erroneous scenario to scale over the system resource limit. Acto generates different scenarios for different properties. And for adequacy, Acto makes sure to cover each property from the operation interface at least once. Third, Acto satisfies the property predicates in the form of control dependencies. An operation does not take effect if the predicates are not satisfied. In this backup example, the backup.storage is only effective if the backup enabled is set to true. Acto infers the dependency using the naming convention for feature toggles. In our experience, operator developers in most of the time name the feature toggles as enabled as the predicates for the sibling properties. For more accurate dependency relationship, Acto uses the control dependency analysis over the operator source code. And for the detailed algorithm, please refer to our paper. Next, with the referred control dependencies, Acto then satisfies the property predicates when changing the property value. For example, Acto sets the backup.enable to true when changing the backup storage property. To automatically check the validity of the system state, Acto checks for explicit error states. For example, unhandled exception, panics, and error codes. However, many operator bugs manifest as implicit state mismatches. To detect the implicit state mismatches, Acto introduces two automatic oracles. First is the consistency oracle. It checks if the operator's view is consistent with the Kubernetes view. Acto also introduces differential oracle, leveraging the level triggering property. It checks if the system can be reconciled to the same end state from different starting states. Next, let me show you a Knative operator bug detected by the differential oracle. Suppose we have an initial system state with no pod. Then a Knative state declaration is applied with the contour ingress disabled. The system state is then correctly reconciled to the desired state, where it only contains the contour pod without the ingress pod. However, if we apply the same state declaration on top of an existing system state, where the contour pod is already enabled, the end state still contains the contour pod. And the differential oracle successfully finds the difference between the two end states. And this is caused by a bug in the Knative operator to failing to disable the contour after the contour is enabled. We designed Acto to be fully automatic. The only required inputs to test the Kubernetes operator is the manifest for deploying the operator with the specification of the operation interface. Both of them are very basic and always available. Optionally, users can provide operator source code for generating more effective state declarations. Acto outputs test failures with detailed information for debugging and reproducing. Since it may take a very long operation sequence to trigger the bug, as an additional feature, Acto produces minimized test code to reproduce the test failure within 2 steps. The minimized test code can then be used as a regression test for the operator. We implement Acto in 2 versions, black box version and white box version. Acto black box is generally applicable to any Kubernetes operators with different implementations. Acto white box performs the additional static analysis for operators we implemented in Golang. Acto runs end-to-end tests on virtualized Kubernetes clusters, supporting different backends, such as Kind, Minikube, and K3D. If you have a very powerful testing infrastructure, Acto also supports test parallelization. It partitions an operation sequence into multiple tests and run them in parallel. For evaluation, we applied Acto to 11 popular Kubernetes operators, and we asked three main research questions. First, can Acto effectively find new bugs in these real-world operators? And indeed, Acto has found 56 bugs in 11 operators. Second, does Acto test operators efficiently? Acto can test each evaluated operator in a nightly run within 8 hours. Third, are Acto's testing results trustworthy? Acto white box has 0 false positive, and Acto black box only has few false positives. Let me show you the main evaluation result, which are the new bugs found by Acto. In this table, each row corresponds to the different operator tested by Acto, and each column corresponds to the different categories of the bugs found by Acto. As we can see, in addition to the bugs which manifest as explicit system errors or explicit operator errors, Acto is also able to find bugs which manifest as implicit undesired states. In fact, this category is the biggest category of the bugs found by Acto, and this shows the importance of the two automatic oracles. Acto is also able to find bugs in operators, preventing them to recover from error states. Acto has found bugs in all the operators it tested, and in total, it found 56 bugs, with 42 confirmed and 30 fixed. To conclude, operation correctness is super important and requires automatic tooling support. We present Acto, an automatic end-to-end testing technique for cloud system operators. We open sourced Acto on GitHub, and we encourage you to take a try. Thank you. I'm ready to take questions.
Hi, great talk, Konstantinos Kalas from UPenn. I was wondering, how do you, maybe I missed it, but how do you find, how do you specify, and do you do it automatically or manually, the undesired states? Because in your final slide in evaluation, you showed many bugs are in undesired states. How are these found, these undesired states?
So the desired states are actually input to the operator, where like the user basically specify the desired states of the system, and the operator is take this desired state and reconcile the system to the actual system state. The desired states are basically the state declarations automatically generated by Acto. And Acto basically exercises various operation scenarios to generate these state declarations.
So the bugs in that column mean that you ended up in a state that was not the desired state. Is that correct?
So sorry, which slide are you?
The undesired state column. This one.
This one, yes.
Yeah.
So in this particular bug category, the system basically, the manifest of this bug is that the system end up in implicit undesired state, where the system did not crash or does not have explicit error states, but then it's actually, for example, it's running in a wrong configuration. It's supposed the declaration has the security feature enabled, but the actual system actually does not have the security feature enabled.
I see. Thank you.
Thanks.
Next question.
Hi, I'm Vastav from Max Planck Institute for Software Systems. My question might be a little bit more philosophical, but could you comment on how you might see this similar to model checking for operators?
Thank you for this very thoughtful question. So basically, you're asking that what is the difference between our technique to the model checking technique?
Or would you label your technique as a model checking technique for operators?
Yeah. So basically, there is actually I actually don't think our technique is a model checking where like because the input space for the operator is huge, where we model basically operations as state transitions, where it's a pair of the current state and the new state declaration, and it's basically the space is a Cartesian product of these two objects, and each object actually has a huge value space. It's going to be prohibitively expensive to exhaustively explore this space. So Acto is actually not doing model checking, where we actually make sure that we cover representative scenarios for each property through our test campaign.
All right, thank you. We
Thanks.
can have an offline chat about that.
Sure, yeah, happy to talk about it.
All right, let's thank our speaker again.